Um, so this is going to be a very easy module, greedy strategy, but it's a very useful module because we use this for several applications every day, as you will see in the problems and examples that we are looking at. So the idea is, so we have seen so far three algorithm design strategies. Brute force in some of the algorithms you have seen in the first module, like bubble sort, insertion sort, they're all brute force approaches. Then we looked at divide and conquer, where you divide a problem into two sub-problems or more than two sub-problems, whatever it is. You solve all the sub-problems or some of the sub-problems and combine the solutions of the sub-problems to get a solution for the larger problem. And merge sort is a good example for divide and conquer. Then we looked at binary search, where we divide the problem search space in the sense that we decide to go, or basically we divide the search space into half, and we decide to go on to either of the two half of such spaces. We don't solve both the sub problems, we solve only one sub problem, and this by deciding which search space, whether the left search space or the right search space, as we used to do. So we solve only one search space and then further reduce the search space size by half in each iteration until the search space becomes too narrow, and by that time you should have found the solution. So that's a binary search approach. So now we're going to look at the greedy strategy. So it's not really having any formal setup like divide and conquer or binary search. The idea is very simple. So again, this is useful for optimization problems, as well as problems that are combinatorial in nature. So from now on, we look at most of the problems that we'll be looking at are what is called combinatorial problems. So greedy strategy and the next strategy we're going to look at dynamic programming, or very good algorithm design strategies for solving combinatorial problems. So what does a combinatorial problem means? We're going to look at several examples, but this is a good example that we can use as reference. Let us say you have a bag, we call this a knapsack, of some weight, 6 pounds. So that's the capacity of the knapsack. The bag cannot hold more than 6 pounds. And you have some items, say 5 items. Each item has some value and some weight. Okay. Now you have to fill the knapsack with one or more of these items, such that the total value of the items you have picked up in the knapsack is the maximum. That's the problem. Okay. So you want to pick one or more items out of these 5 items, such that the total value of the items you have picked up in the knapsack is the maximum. So of course you would try to fill as much as possible and use all the available capacity of the knapsack. Okay. Now it depends on what items you pick. Of course, none of the items are exactly 6 pounds, and that item is not having the largest weight. So you have items of smaller weight. So you have to pick, of course, 2 or more items. So what combination of items you would pick, so that the total value of the items you have picked up is the maximum. You cannot just pick any 2 items or any 3 items. It depends on what combination you will choose. So if you do this with a brute force approach, you have to write down all possible combinations. Should I pick 1 with 2, 1 with 3, or 1 with 4, 1 with 5? Or should I pick 1, 2, 3, 1, 2, 4, 1, 2, 5? Or 1, 2, 3, 1, 4, 1, 2, 3, 5? Different combinations, you see. So it becomes like an exponential problem, and you don't want to spend exponential amount of time to solve a problem. So we want to find the optimal solution. That means we want to find what combination of items will give us the maximum value that anyone can pick up for this knapsack of given capacity and is given 5 items. So you want to find the optimal solution. You want to find what's called the global optimum. Global optimum means overall among all these 5 items, which is the what combination of items we'll pick so that we get the maximum value. So that's the nature of the problems, combinatorial problems. What combination of items that you have to choose for the optimal solution. Now, again, if you look at this problem, one approach as a greedy strategy would be pick that item that by itself has the largest value, and then go about picking items in the decreasing order of their values. So if you go by that strategy, 50 is the maximum value of any item and the corresponding weight is 5. So you will pick that item of weight 5 and you fill it in a knapsack of capacity 6 pounds. So you have space available for only 1 pound. So if the items cannot be broken, you have to take either the entire item or just leave the item. Then your only choice is picking item 3 of weight 15, of value 15. So you would have picked up 6 pounds and the total value would have collected is 65. Now you may be wondering, is that the maximum possible? Okay. For this combination of item weights and values, it appears that itself is a maximum 65. But you will soon realize that what if this weight is this value is instead of 15 some 5, then you would have ended up picking up 50 plus 5, 55 instead of 65. Okay, so it's a greedy strategy. By picking the item that has the largest value among the items that we have so far, and then go based on that. So, and also there is a restriction that you cannot pick more than 1 copy of the same item. So if you pick item 5, that's it. You cannot pick another copy of item 5. It's only one instance of each item, because you will see several problems with different restrictions. In some problems you could pick same item again and again. Okay. So as you see, that the strategy we came up with is just pure common sense. Just pick up the item that has largest value among the items, and then based on that go further picking up the items. But you see here in this particular strategy which I just mentioned, once you pick up the value, the item with the largest value among the items, which is 50, you are forced to pick this item 3. Okay, so your greedy strategy may sometimes force you to narrow down to only certain items. And if the greedy strategy does that, it's not a good greedy strategy. It's not a good strategy. Okay. Sometimes greedy strategy has that weakness. You may initially start very positive, very promising. Like in this case, I picked up the item that has the largest value among all the items. So you may think you're approaching the optimal solution, the global optimal solution. But that will make you to narrow down to only to some suboptimal solutions, not the optimal solutions. So the greedy strategy has such a weakness. Okay. So when we go through this problem, we look at a particular greedy strategy that is guaranteed to give you the optimal solution all the time, irrespective of their values. If you apply this strategy, you're guaranteed to find the optimal solution for any weight and values. Okay. But remember that problem with greedy strategies, it may sometimes lead you to suboptimal solutions. But we don't have to really do any complex thing like binary search or divide and conquer or the other approaches you're going to see, dynamic programming. So the time complexity of greedy strategies are going to be mostly very less time consuming. So it's less time consuming, but depending on the strategy, it may sometimes lead you to optimal solution, but sometimes not. We'll look at one more example, which is also a common sense kind of thing. The coin denomination problem. Okay, so like if you go to a grocery store and you want change for some value, say in cents. So let us say you want to change for 48 cents. you would expect the grocery store person to give you the change with as few coins as possible. You don't want that person to give you all 48 1 cent coins, which is called penny, right? So you don't want them back to give you back 48 coins. You want them to give you back as few coins as possible and make up for that 48 cents. So if you look at what strategy should that person come up to decide what's the minimum number of coins and what combination of those coins to give you back, there's a greedy strategy behind that. So let's do it now. So you see there are 4 different coin values in US. 25 cents quarter, and then 10 cents called a dime, 5 cents nickel, and 1 cent is a penny. So you write this down like this. This is also similar to the binary conversion approach, which I think most of you know. So that's why I'm picking this example. So these are the 4 coin denominations, and you want to get change for 48 cents. So what you do is you want to again minimize the number of coins to represent 48 cents. So as a greedy approach, it looks like if I go with as many 25-cent coins as possible, I can minimize the number of coins I can have. And so let us try that. So you cannot pick 2 25-cent coins because that will be like 50 cents. You want to give change for only 48 cents. So you can pick only 1 25-cent coin. So the balance is now 48 minus 25, which is 23. So you have to find the number of coins needed to give 23 cents back. You cannot pick again another 25, so the next choice would be to pick 1 or more 10-cent coins, and you want to give change for 23 cents. So you could pick 2 10-cent coins that will make up 20 cents, and the balance is 3 cents. So now go for a 5-cent coin. You cannot go for any 5-cent coin because you want to give change for only 3-cent coins, and then your only option is to go for 3 1-cent coins. So totally you need 6 coins, and that's the best we can do. We cannot go less than 6 coins for 48 cents in the US with these 4 coin denominations. Now, is it guaranteed to give you the optimal solution? The answer is yes, provided these are the 4 coin denomination values. And also there's an implicit assumption here. You can pick any number of coins for a particular denomination. You can pick any number of 10-cent coins as you need. So there's an assumption. Unlike the knapsack problem, here you have infinite supply of each coin. Okay. So why I said it has to be this 4 coin denominations to apply this particular strategy of picking as many coins as possible, starting with the largest value and then go further down. Okay. So why I said that is, so let us pick some other coin denomination. Let us say it is 25, 10, 1. 25, 10, 1. So these are the 3 coin denominations you have, and let us say you want change for 30 cents. Now if you want to apply the strategy of picking the largest coin with the largest denomination as much as possible, let us try that. We can pick only 1 25-cent coin, so that means you have now to provide change for remaining the balance, which is 5 cents. So you cannot pick any 10-cent coin. Okay, so that means you have to pick 5 1-cent coins. So the total number of coins you would need is 6 coins. Whereas you would have realized by now the optimal solution would be to pick 3 10-cent coins to make up 30 cents. So picking 3 coins is the optimal solution, and 6 is not the optimal solution. So for this combination of coin values, the greedy strategy really fails. Okay. So you see, in both these examples, the greedy strategy is kind of narrowing down your choices. Like here, after you pick the coin with value 25 cents, you could pick 2 10-cent coins, but you cannot pick any 5-cent coins. You are forced to pick up 3 1-cent coins. And here it is even more obvious. After picking one 25-cent coin, you cannot pick any 10-cent coins. You have to pick the one cent coins 5 times. So this choice of picking one 25-cent coin kind of narrows down your choices and leads to suboptimal solution. If you did not pick up any 25-cent coin, you could have picked up 3 10-cent coins and found your suboptimal solution. So the greedy strategy has this kind of weakness of not guaranteeing optimal solution for some problems. So it depends on the problem and depends on all these what you call particular cases, what coin denominations, like in this case. Okay. Now we'll come back to this coin denomination problem in the next module on dynamic programming, and there, using the dynamic programming approach, we can find out the minimum number of coins for any coin denomination. It need not be the coin denomination that we have in US, for which the greedy strategy guarantees the optimal solution. It could be any coin denomination, and we will be able to find the optimal solution using dynamic programming. But we'll be spending more time compared to the time we spent here for greedy strategy. Okay, so that's like a trade-off. Now, the first example I have put here is something you should have come across already. The problem of representing an integer in binary. So again, one implicit objective there is to minimize the number of ones in the binary representation of any integer. So that is why you write down the exponents of 2, say 1, 2, up to, say in this case you want to represent 75 in binary, so there's no point in going beyond 64, so we stop at 64. And then using the same approach in the coin denomination, we'll try to fill up with ones and zeros such that you cover as much as possible within the 75, starting from the most significant bit value, which is 64. So 64 can fit within 75, so you put a 1 here, and the balance is 75 minus 64, 11. So you cannot put 1 here for 32 because we want to represent only 11 now in binary. So you put a 0 for 16 also, but 8 is less than 11, so you can put a 1 there. So that means you have to represent only 11 minus 8, which is 3 in binary. So you have to put a 0 for 4, and you have to put a 1 for 2 and 1 each. So this is the binary representation of 75, and it comes out to be also the representation that guarantees you the minimum number of ones. So it depends on the problem. It sometimes gives you a good, better, optimal solution, but sometimes some suboptimal solution. Okay, so this is kind of like an overview of greedy strategy, and we'll go through some specific algorithms now. Any questions so far? So let me see.